You know that universally frustrating experience where you're just working away on your computer?
Oh, yeah, I think we all know where this is going.
Right. So you click a button to save or maybe submit something, and suddenly, like, everything just freezes.
The dreaded freeze.
Exactly. Your cursor turns into that little spinning wheel of doom, and the fan inside the machine starts whirring louder and louder. Like it's trying to take off from your desk.
Yeah, sounding like a jet engine.
Right. You tap the keyboard and just nothing. There's no crash, no error message telling you what went wrong. It's just a completely frozen screen.
It's infuriating.
It totally is.
Yeah.
But, underneath that frozen interface, your computer is actually actively fighting this completely invisible war.
It is, yeah. And it's a phenomenon programmers actually call a deadlock.
A deadlock.
Right. And to see how a machine gets backed into this corner, we are taking a deep dive today into this incredibly creative, narrative-driven piece. It's by Aaron Rose over at tech-reader.blog, and it's called The Secret Life of Python - The Deadlock.
It's such a great piece.
It really is. And, even if you have never written a single line of code in your life, our goal today is to unpack this logic, because understanding the logic behind these digital gridlocks and, crucially, like how software engineers solve them, it will completely change how you view problem solving in literally any complex system.
Yeah, it's so much bigger than just computers.
Yeah.
And this silent freeze is exactly what happens to a junior developer named Timothy in Aaron Rose's piece.
Right. Poor Timothy.
Yeah. The author drops us into this fascinating setting to start off. It's this grand Victorian library in London. So imagine, like, towering bookshelves, quiet mahogany study tables, rolling ladders.
Sounds very cozy.
Right. But it's not a normal library. It's actually a software engineering hub where code quality is the unspoken objective and craftsmanship is, the absolute highest priority.
Yeah, the architecture of the code in this library is treated with intense respect. I mean, it's almost sacred. And in this environment, we meet two software engineers. So there's Margaret, who is this wise, seasoned senior engineer. She's seen every bug imaginable.
A veteran.
Yeah. And then there's Timothy, her junior colleague. And he's ambitious. He's learning fast, and he's feeling pretty confident right now because he's just started tackling this complex programming concept called concurrency.
Right, concurrency, which is basically getting the computer to do multiple things at the exact same time,
Right.
rather than, waiting in a single file line.
Exactly, doing things simultaneously.
So Timothy is building an app for a chess club, and he needs to execute a task called a transfer. He has two digital wallets in his program. One is the entry fee vault, and the other is the prize pool vault.
Pretty standard setup so far.
Yeah, the business logic seems simple enough, right? When a player wins a chess match, a piece of code basically takes money from the entry fee vault and moves it to the prize pool vault.
Right, but the challenge Timothy faces is that, well, a busy chess club might have dozens of matches ending at the exact same millisecond.
Oh, wow, dozens at once.
Yeah. So if the computer's doing things simultaneously, the code might try to move money out of the same vault at the exact same time for two different winners.
Wait, if we don't put any protections on those vaults and the computer is processing two transfers simultaneously, like, what actually happens to the money? Do things get overwritten?
Yes. Software engineers call that scenario a race condition, and honestly, it is a financial nightmare.
I can imagine.
Let's say the prize pool vault has a balance of $100. Match A ends. And its code looks at the vault and says, okay, the balance is 100, I need to add 50.
Makes sense.
But in that exact same split second, match B ends. Its code looks at the vault, also sees the original $100, and says, hey, I also need to add 50.
Oh, I see the math problem here.
Yeah.
So match A adds his $50 to the 100, making it 150, and writes that back to the vault.
Yeah.
But match B, which still thinks the original balance was 100, adds its $50 and also writes 150 to the vault.
Exactly.
We should have $200, but we only have 150. $50 just vanished into thin air because they literally wrote over each other.
It just disappears. And that is the exact reason why locks exist in programming. To prevent money from vanishing or, duplicating, a programmer has to guarantee that only one process can touch a vault at a time.
Right.
So the source material explains that to keep the transfer secure, or thread safe, as they call it, Timothy decides he must lock both vaults before any money moves.
Okay, let's unpack this. Let's look at Timothy's master plan for locking things down, because he sets up a test run. Match A is finishing up, and its computer process, which we call thread A, needs to transfer money from vault 1 to vault 2.
Right.
But at the exact same time, match B finishes. But it's thread B needs to transfer money in the opposite direction, right?
Right.
From Vault 2 back to Vault 1.
Yeah, so Timothy writes a function to handle this securely. For match A, thread A is instructed to lock Vault 1, then lock Vault 2, make the transfer, and finally unlock them both.
Sounds logical.
It does. And then for match B, thread B is instructed to lock Vault 2 first, then try to lock Vault 1, transfer the money, and unlock them.
Okay, so it's basically like, I want to borrow your car keys to run an errand, right? And you are waiting at my house to borrow my house keys so you can get inside.
I love this analogy. Yeah.
But neither of us is willing to hand our keys over first. I'm gripping my house keys tight, saying, give me the car keys first, then I'll let go.
Right.
And you're holding the car keys tight, saying, give me the house keys first. If we both lock our grips on our first set of keys, we just stand there glaring at each other forever. Neither of us ever gets the second set.
Exactly. Your standoff perfectly describes the disaster that strikes when Timothy runs his code. The logic of grabbing the first available resource completely backfires when multiple processes are working in opposite directions.
So Timothy hits enter on his keyboard to run the test. The computer screen prints out 2 lines of text. It says, thread A, locked Vault 1, waiting for Vault 2. And right below it, thread B, locked Vault 2, waiting for Vault 1. And then absolutely nothing. The program doesn't crash. The window doesn't close. The computer fan just starts spinning louder and louder. Timothy is just sitting there in this grand Victorian library, whispering to Margaret like they're just staring at each other. Neither one will move.
It's such a visceral moment in the piece. And that's when Margaret steps in with the diagnosis. She tells Timothy that he has created a deadlock.
A deadlock.
Yeah. She describes it as the ultimate Mexican standoff. In the source, Margaret actually draws 2 circles on a board to explain what she calls the circular wait.
The circular wait.
Right. This is the core mechanic of a deadlock. Thread A has the key to Vault 1, and its programming dictates it absolutely cannot release that key until it gets the key to Vault 2 and finishes its job.
Meanwhile, thread B is holding the key to Vault 2, and its programming dictates it cannot let go until it gets the key to Vault 1. They're both waiting for a door that the other person has locked from the inside.
Precisely. And since neither thread is capable of dropping its lock until the transfer is finished, and they cannot possibly finish the transfer without the other lock,
They just stay stuck.
they will stay in that exact spot indefinitely.
But wait, why doesn't the machine just step in? Like, I can look at 2 people stubbornly holding keys and realize they are stuck. Why doesn't the computer just realize it's jammed up, throw a big red error message on the screen, and quit the program so the developer knows there's a problem?
Well, we often anthropomorphize computers, right? Assuming they have some level of common sense or like a bird's eye view of their own operations. But computers are flawlessly, blindly obedient to their immediate instructions.
So they don't see the big picture.
Not at all. The individual threads, thread A and thread B, they do not know they are in a standoff.
I mean, thread A doesn't even know thread B exists, right?
Exactly. All thread A knows is its current line of code, which is wait for Vault 2 to open. It assumes Vault 2 is just temporarily busy with another task and will open eventually. It is faithfully, patiently waiting for a door that happens to be locked. And the reason the computer fan is spinning up so loudly is that the CPU isn't actually resting.
Right, because it's checking the door.
Yes, it is rapidly checking that door millions of times a second, asking, is it unlocked yet? Is it unlocked yet? It's burning massive amounts of energy while making 0 actual progress.
You know, a bug that crashes your system loudly with a big error message is incredibly annoying, but at least it leaves a footprint. It tells you, hey, I broke, and here's exactly the line of code where I broke.
Yeah, a loud failure is easy to fix.
But a bug that just lurks silently and freezes your machine while looking completely normal, that's a massive drain on an engineering team. You don't even know where to start looking because the computer thinks everything is fine.
It's terrifying. Margaret actually has a philosophy about this in the source material. She calls deadlocks ghosts.
Ghosts.
Yeah, ghosts. Because they only appear when the timing is exactly catastrophically wrong.
Oh, the timing aspect is the trickiest part of all of this. Because, like, if thread A was just a fraction of a millisecond faster, it might have grabbed the lock for Vault 1 and the lock for Vault 2 before thread B even woke up to try.
Exactly. In that scenario, thread A finishes its job, puts both keys back, and then thread B takes its turn. It grabs both keys, finishes, and everything works perfectly.
So it looks totally fine.
You could run this exact same code 99 times in a row during testing, and if the timing is even slightly staggered, the transfer executes flawlessly.
And then you push the code out to the real world, thinking it's completely safe.
Yep. And on the 100th time, under the heavy load of a busy chess club, two threads happen to grab their first locks at the exact same microsecond, and boom, the entire application freezes.
That is wild. So how do you even track down a ghost then? If there's no error message and the program just hangs there silently spinning the fan, how do software engineers look under the hood to figure out what's happening?
Well, the author provides Marvin's cheat sheet for detecting this silent threat.
Okay, good. A cheat sheet.
Yeah. If your program freezes with no error, your first step is to manually interrupt the execution. You hit Control-C on your keyboard.
Just force it to stop.
Exactly. When you force the program to violently stop its endless waiting loop, Python will spit out what is called a traceback.
Right, and a traceback is essentially a snapshot of the crime scene. It's a log of exactly what every single thread was doing at the exact millisecond you killed the program.
That's a great way to put it. And Margaret's rule for reading that snapshot is really simple. If you look at the traceback and you see that your threads are stuck waiting at a command called lock.acquire, you've caught the ghost. You have a deadlock. They were stuck trying to acquire a lock that was never going to become available.
So Timothy uses Control-C. He sees lock.acquire all over his traceback, and he knows he has a Mexican standoff with his vaults.
Yep, he caught it.
But knowing you have a circular wait isn't the same as architecting a system that prevents it from ever happening again. So he asks Margaret how to fix his abundance of keys, and she gives him this foundational rule of system design.
Yes, she introduces the primary defense against deadlocks. She calls it the golden rule, which is lock ordering.
Lock ordering.
Right. If a program has multiple locks, every single thread in the entire application must acquire those locks in the exact same order. Always. No exceptions.
So even if the money is flowing backward from Vault 2 to Vault 1, the rule dictates you must always lock Vault 1 before Vault 2.
Always.
Both threads must attempt to grab the lock for Vault 1 first, regardless of their ultimate destination.
Let's walk through the newly fixed scenario from the text with lock ordering applied. So both threads wake up. Match A wants to move money from 1 to 2. Match B wants to move money from 2 to 1.
Okay.
But because of the new strict lock ordering policy, they both must try to grab lock 1 first. Let's say thread A gets there a microsecond faster and grabs lock 1.
So thread B tries to grab lock 1, but thread A already has it, which means thread B simply waits at the first door. It hasn't even touched lock 2 yet.
Exactly. And because thread B is waiting patiently at the first door, lock 2 is completely unguarded. So thread A, holding lock 1, happily reaches out and grabs lock 2. It has both locks. It finishes its transfer, updates the balances safely, releases lock 2, releases lock 1, and goes home.
And now thread B, which was stuck in line at the first door, finally grabs lock 1, then it grabs lock 2, finishes its job, and releases them.
Yeah, the standoff never happens.
It's basically making the grocery store aisles one way.
Oh, that's a good way to look at it.
Yeah, if everyone enters the aisle from the same end and pushes their cart in the same direction, nobody ever gets stuck head-to-head in the middle of the aisle. I mean, you might have a bit of a line at the entrance, but the flow of traffic is guaranteed to keep moving.
That's perfect, yeah. And if we connect this to the bigger picture, Margaret actually drops a piece of profound wisdom here as Timothy watches his newly ordered code run flawlessly.
What does she say?
She tells him that as a software engineer, his job isn't just to lock things down to keep them safe. His job is to design a clear path of entry.
Path of entry.
Right. You have to architect the flow of your system so that different processes never end up reaching for each other's throats. Establishing a strict, predictable sequence of operations removes the possibility of a circular wait entirely.
Right, but sure, a one-way aisle works perfectly for a tiny chess app with 2 vaults. But what if you are dealing with a massive tech platform?
Oh, right.
I mean, what if it's not just 2 vaults, but thousands of different databases, servers, and resources? You cannot realistically map out a perfect sequential lock order for thousands of interconnected resources without someone eventually making a mistake or creating a bottleneck, right? Does Margaret's cheat sheet have a fallback plan for when strict ordering breaks down?
That is a very real problem, and the source material addresses this reality head-on. Strict lock ordering is elegant, but it just isn't always feasible in highly chaotic distributed software architecture.
Too many moving parts.
Exactly. And that leads us to the final failsafe on Margaret's cheat sheet, which is the timeout strategy.
Okay, the timeout strategy.
Yeah. Instead of a thread blindly waiting forever for a locked door to open, you introduce a strict time limit. So the code snippet the author provides is lock.acquire, parenthesis, timeout equals 5.
Ah, so We're giving the computer a 5-second patience limit.
Right.
If the thread wants a key, it tries to grab it. If the key is locked by someone else, the thread basically says, well, I will wait, but only for 5 seconds.
Exactly. And if those 5 seconds expire and the thread still cannot get the key it needs, it does not crash the system. It executes a tactical retreat.
A retreat.
Yeah, it willingly drops any locks it already holds, steps back, and essentially says, I'm going to stop blocking traffic and try this whole process again later.
Wait, if it drops the locks and walks away, does the transfer fail? Like, does the chess winner just not get their prize money because the computer gave up after 5 seconds?
Oh, no, the transfer doesn't permanently fail. It just gets queued for a retry.
Oh, I see.
Yeah, in modern system design, when a thread hits a timeout and drops its locks, the overarching program catches that timeout and places the transfer request back into a pending line. The thread basically says, I couldn't get the resources I needed this time. Let me go to the back of the line and try again in a few milliseconds.
That is brilliant.
Isn't it?
Yeah, by dropping whatever it's holding, it breaks the circular wait. The moment thread A drops the key to Vault 1 because its timer ran out, thread B, which was waiting for Vault 1, can finally grab it, finish its work, and the system keeps moving.
Right, it's essentially a pressure release valve. Instead of freezing forever in a standoff, one of the processes just gets tired of waiting, puts its weapons down, walks away, and agrees to try again later.
It gracefully backs away before the circular wait can become a permanent freeze.
Exactly. It is a highly effective plan B when you just cannot guarantee a perfect one-way path of entry.
Man, this has been such a revealing journey into the mechanics of the machines we use every day.
It really is fascinating under the hood.
It is. We started with that universally frustrating frozen computer screen. You know, the fan spinning, the cursor stuck, nothing happening. And now we know that underneath that silence, there's likely a Mexican standoff happening.
Yep.
A deadlock fueled by a circular wait, where two blindly obedient processes are locked in a permanent standoff, waiting for resources the other is holding.
And thanks to Margaret and Timothy and their Grand Victorian Library, we also have the conceptual tools to break those standoffs.
Right.
We know that the most elegant fix is the golden rule, which is lock ordering, creating that clear path of entry so threads acquire resources in the exact same sequence every single time.
And if the system is too messy for a perfect sequence, we have the timeout strategy, the tactical retreat of dropping your locks and returning to the back of the line to prevent the whole system from paralyzing.
Exactly. And, you know, even if you never write a line of Python in your life, the concepts in this article offer a profound masterclass in system design.
They really do.
Deadlocks teach us that complex systems often fail, not because the specific part physically broke, but because of conflicting rules.
Conflicting rules.
Yeah, they fail because the architecture allowed two entities to hold on to resources stubbornly without a clear path forward. Creating a clear path of entry isn't just about Python code, it's about preventing chaos in any environment where multiple things are competing for limited resources at the same time.
Absolutely. So, what does this all mean for us outside the glow of the computer screen? I want to leave you with a final thought to ponder today.
Ooh, okay.
If purely logical, flawlessly obedient machines can become completely paralyzed simply by waiting for each other to make a move, how often do our own human systems suffer from the exact same bug?
That's a great question.
Right. Think about your cross-department team workflows, your stalled office meetings, or, I don't know, even your personal relationships. How often are we stuck in an invisible deadlock waiting for someone else to act while they wait for us to act, simply because we haven't established a clear path of entry, or given ourselves a 5-second timeout strategy to just drop our defenses, step back, and try again from a different angle?